All right, good afternoon, everybody. It's time for another wrestling stream today. I think today's going to be a little bit different in that it's coming from just some random code that I saw on the internet. There was a question on one of the Rust forums out there, or on Zulip, I think it was. Somebody asking a question about how to do something that actually involved a somewhat nuanced understanding of lifetimes, and I'm constantly on the search out for good examples of lifetime problems. The fact of the matter is that in wrestling, lifetimes get a lot of attention because it's a newer concept. No other language really has the concept of lifetimes kind of baked into it like Rust does, and so it's something that people struggle with, very understandably so, because it does require an understanding that you wouldn't necessarily get from other languages, with the possible exception of C and C++. Although there, because it's not baked into the language, it's kind of more of a cursory understanding, and when it's formalized in Rust, that might lead to some gnashing of teeth. And with that, I'm always kind of looking for good examples to teach concepts about lifetimes. But the fact of the matter is that most of the time when you're writing Rust, you don't usually have to think too deeply about lifetimes, especially about explicit lifetime annotations. You do have to think about lifetimes and ownership and borrowing kind of at a high level, but you're most of the time not annotating that in your code. But when sometimes you do have to annotate it, and when that happens, you usually end up with some code that maybe is not super understandable if you're coming at it with fresh eyes. And so I thought today we would basically go through this example that I found that I think is extremely simple in and kind of what it's trying to achieve, but should be take very little time to explain what we're trying to do, but requires kind of a deeper understanding of lifetimes. And the hope with that is that we can kind of talk through some things and get a better understanding. And what I'm really hoping is maybe there's somebody who has an extremely deep knowledge of lifetimes beyond what I even have, who can explain some of these things in really formal terms, because some of it is a little bit of the compiler kind of helping us out in not necessarily magical ways, but ways that are kind of a little bit, might be a little bit difficult to understand when we first look at it. Okay, I've been talking too much. So let's switch on over here to my screen. We're just going to go ahead and create a new project as we normally do, and I'm going to call it Lifetimes, and I'm going to make it a lib. And then I'm just going to open it up in VS Code so we can go ahead and get started. All right. So, I think we will write a few tests just so we can get a better understanding of what exactly is happening. Real quick, but the code should be pretty straightforward to understand. So what do we want to actually accomplish today? Well, the code that I saw on Zulip was basically trying to create an iterator over a slice of elements of type T, basically. So basically, you have a collection of things. You're borrowing that collection, and you want to iterate over that collection. And the key to this is that you want to iterate over that collection in a mutable way. So you want to basically point to each element in that collection and give a mutable element into it. Now, most things in Rust already implement iterator, so this isn't really necessary to do. But basically what we want to do is, if we say have something like our collection here, and it is 1, 2, 3, 4, And for simplicity, let's go ahead and just make this a vector real quick. And then we want to do something like, you know, for lm in collection dot iter underscore mut. And this iterates over the elements and gives us a mutable reference to each element in turn. So this is kind of what we want to implement, but we want to write a wrapper around our type and basically implement the iterator trait for ourselves. Does that make sense to everybody? Let me know if that makes sense to all of you. And but I think as we write the code, this will become clearer. So basically, I thought instead of starting out with a mutable iterator, which is you know, going to be a little bit non-trivial, we should start with a non-mutable iterator, and that might help us kind of get up to speed with what we're doing. So basically, I want to write a struct called myIterWrapper, and this struct is going to wrap a collection of some sort, a slice of some sort, so we can just call it slice, of type T, just like this. All right, so we have this struct. It has one field called slice, and that field slice is of type slice of T. Now, of course, this is not going to actually compile here. Let's see if I can go ahead and get it to. So the first thing that it's saying is that it's missing a lifetime specifier. This is purely kind of a syntactic thing in Rust, where when you have a field that is a borrow, you need to specifically say what is the lifetime of that borrow. How long will that borrow last for? And Chad has asked, so you're essentially implementing another way that an iter_mut works behind the scenes. Yeah, we're basically writing a wrapper and writing iter_mut ourselves on top of it. So here we need to specify a lifetime, and by convention, usually lifetimes are tick A in Rust, but we can call it whatever we want. And in fact, today we're going to be taking advantage of that fact. And it's saying, I don't know what tick A is. What are you talking about? That lifetime has not been declared, and that's true. We have to say that our struct is generic over lifetime A. And this is an important point that I think a lot of people don't think about. Essentially, what we're doing here is tying the myIterWrapper struct, how long that struct can live for, its lifetime, because everything in Rust has a lifetime. We're tying it to whatever the lifetime of the inner slice is. All right. And Chad is asking, I'm wondering how this is going to work without unsafe. It is possible to do this without unsafe. So I believe it's only possible in Rust 2018, which I've recently found out 99.9% of people use Rust 2018. So yes, it should be possible. So we've tied the lifetime of our myIterWrapper struct to the lifetime of the slice that's inside of it, which makes sense, right? This struct can only live as long as we have a valid slice inside of it. So we can't have a slice that doesn't live as long as the struct that wraps around it. Why? Because if that were the case, then we could have a myIterWrapper struct with a slice that's not valid anymore, and that's not possible in Rust. We don't want that. That's what Rust is designed to prevent us from having. All right. Cool. It looks like we have a solution in chat, so hopefully we can compare those solutions and see what they look like once we get to that point. Because I believe there's multiple ways to do this. The last error that we see here is that we can't find the type T. So we need a way essentially of making this generic over some type T, and that's quite easy, right? So myIterWrapper struct is generic over some lifetime tick A and some type T. So that's great. What is this complaining about? Oh, this is complaining that it's not mutable. All right. So we want to be able to write this essentially. We have a collection here, and we want to say wrapper is my iter wrapper, where the slice is a slice on the entire vector collection. What is it? Oh, and we gotta bring my iter wrapper into scope so we can actually refer to it by this use super here. And then what we want to be able to do is iterate over it and say like this. And we're going to get an error here saying that my iter wrapper is not an iterator. All right, so this should be able to, we should be able to compile this code here. So we need to implement iterator on my iter wrapper. So impl iterator for my iter wrapper. And now we have to say, okay, my iter wrapper is generic over some lifetime tick A here and some type T. Now this will complain here because it doesn't know what tick A is and it doesn't know what T is. It's looking for a actual lifetime that it knows about called tick A, which there isn't one, and it's looking for a type called T, and there isn't one. So we need to say that those are two generic things, which is how we do that here. Say, hey, we've got two generic types, tick A and T, and we're going to use them in these positions. All right. And we're getting a complaint here saying that we're missing a whole bunch of stuff. We're missing item and we're missing next, which is what iterator expects when we implement it. So let's go ahead and do that real quick and say the type item, which is the type of thing that we iterate. So on each turn, we iterate and provide an element. We provide a reference to type T. And of course, it's going to complain again here saying, I don't know, I need to know how long this reference lives for. And so we can say that the reference is going to live for tick A. So essentially, now we've tied three things together. We've said that my iter wrapper lives for as long as the slice lives for, and the element that we kind of yield out to people on iteration will live for as long as my iter wrapper does. They're all living for the same lifetime, tick A. All right, and it's still complaining because we're missing the next function, which is how iterator actually iterates and yields new items. So iterator, each time we iterate, we call this next function, which yields out the next item. And we're getting a question in chat here that I think is a great question. It's a question that comes up quite often. Like they're asking the syntax differences between the generic parameters on structs and the generic parameters for an implementation here. Why is there a difference? Like, why do we have to first declare tick A and T here before using them here? And the reason for that is because if we remove this syntax also has meaning. This is totally valid Rust code. It is simply looking for parameters, type parameters here that already exist. So it's looking for a lifetime parameter tick A that should already exist in scope, which there is none that exists in scope. There is no concrete lifetime parameter tick A. In fact, there is only one lifetime parameter that actually exists that is not generic, is tick static. And also it's looking for an actual type T. but there is no type called T. There is no type that exists called type T. It is generic. So we first have to say that tick A and type T are two generic parameters that we're declaring for this implementation here, and we're going to use them here. This is important because we could actually implement iterator. We could, if we comment that out, we could say we're going to implement an iterator that only works for static lifetimes where the element is in I32. And of course, this will complain because we're not actually implementing it, but this is totally valid because there is a concrete lifetime tick static and there is a type I32 here. So I hope that that answers that question. Up in struct, this is just where you put the generic parameters, because it's possible to make something generic over concrete types. That doesn't really make sense. So I hope that answers your question. Let me know if that's still not satisfying, and I can try and go at it from a different angle. All right. Cool. So let's go ahead and see if we can get further with this. The first thing that I usually like to do is get things compiling. So I put in the to-do macro here, which basically says like get the thing to compile, and if I run this, crash the program. That's very helpful. So everything is compiling here. If we were running this, it would simply just crash. That's all. But this is fine. This works. So let's go ahead and think about how we want to do this. What we want to do is essentially every time we iterate, we want to get the first element of the slice, and then set slice to be equal to the other elements in the array. All right. So first, get the first element, then set the other elements as self.slice, and then return first element. All right. So how do we get the first element? Well, that should be pretty straightforward. We can just do slice, self.slice get, and 0 indexed here, of course. So this returns back to us an option, which is great. It returns to us an option because the slice might be empty and the first element in the slice might not exist. So that's why it's returning an option here. Now we want to set the other element, like self.slice, to the other elements. Let's write it that way. Set self.slice equal to the other elements. This is essentially like popping off the first element and saying that self.slice is now equal to the tail of that thing. So we can simply say self.slice is equal to self.slice one ... and we got to borrow that. So this syntax is a little funky here, but this is essentially saying take every element starting from the one index element, so the second element in the list, all the way to the end. Because we're doing one ... and not providing an end, so that is assumed to be the end of the list here. All right, and we're setting that equal to self.slice. So now after this point, self.slice is equal to whatever was at the end, what was ever equal to the second element in the list all the way to the end of the list. And good point, that's not a spoiler, that's what I was going to talk about just now, chat, so thanks for that. This will panic, though, if we have an element that, or we have a slice that's empty, because when we index into a slice and we try to get the element at position 1 and beyond, if there is no element at that position, it will panic. So we need to have a shortcut here, basically saying like if self.slice is empty, return none. And that should work. And with that, we can just return the first element. And we already have to return an option here, so the types line up great here. We should expect this to, like, if we want to make sure that nothing weird is going on, we can do something like this where we unwrap it and then rewrap it in some. Oops, rewrap it in some, because element here should always be set, because we're guaranteeing that there's one element in the slice with this check up here. But there's no need to do that. That's just extra work. So we'll just do this. And this compiles just fine. And I hope, let's actually write in the test, like, we can actually do this. Index. This should work fine. We can assert that elem is equal to collection index. What is that complaining about? Assert equal, sorry. Still complaining. Because we need to dereference the two. So if we go ahead and do cargo test, it passes. Great. Cool. So we've successfully implemented a wrapper type that basically wraps our slice and provides an iterator over it. Not super exciting because we simply could have just called .iter on our vec and done the same thing. But now we know how iterator works. We declared a type, item. That type is a reference to an element of type T. It has a lifetime of type A. That lifetime ties however long the element lives for to however long my iter wrapper lives for, which itself is tied to however long the slice inside of it lives for, which again makes sense, right? We don't want to we don't want to iterate over a collection, hand out references to elements inside of the slice without knowing if that element might live longer than the slice itself does, right? If that were the case, then we might end up in a situation where we have a reference out somewhere, the slice is no longer valid, and we have a dangling pointer, and we can't have that in Rust, right? So this works. This is probably what you understand if you've come to good terms with Rust borrowing kind of 101. So we're going to stop here for just a second and see if anybody understands or anybody has any questions about what's going on here. And apparently there is another way, which I didn't know about this. There's another function that we can try to do the exact same thing here, but in kind of it's actually the same amount of lines. It's actually more code, but let's do that real quick because that will help us figure out some code that's coming up later. There is a self.slice.split first, and that gives us element and rest. It's option, okay. So we can do this actually. Oh, this is great, yeah. So here we call split first on the slice, and split first gives us the first element and the rest of the list. And it will return an option if there is no first element, which is really great. And now, since this is returning, it's wrapping it all on an option, we can use question mark to just say, if it's none, return early with none. And then all we have to do here is self.slice is equal to rest. And we got a wrap. So this does exactly the same thing. But you know, you can pick which one you like better. So, and then we're getting a question, why are we mutating self.slice in place? Does that make it so we can't iterate over a wrapper more than once? That is true, yes. And that is what an iterator is. Iterators are, you can notice here, the iterator trait, you pass in ampersand mut_self here. The reason for that is iterators are essentially meant to iterate only once. So we iterate, and then we'll eventually reach the end of the list, and we can't reuse our iterator. We'll have to reconstruct a new iterator. And that's essentially how iterators work. The reason for that is a lot of times, if you want to do iteration, you have to keep some internal state here, which that's what we're doing here, right? We're keeping internal state here. But notice we're not mutating the slice itself. We're not changing the slice itself because it's an immutable reference itself, right? So we're not changing what this is pointing to. Where those elements sit in memory, they're not being changed at all. We're simply changing what self.slice is pointing to. We're essentially changing the pointer. Yeah, and as Chad is saying, it's basically just kind of shifting a pointer forward and saying, okay, we were originally pointing to the beginning of the list here. Now we're pointing to the first element, then the second element, then the third element, and on and on. So when you set slice to the next elements, can you give a bit first? So there's a question about, is this a costly operation? No, it shouldn't be. The reason for that is when we call split.first, essentially what it's doing is giving us two pointers. So references at the end of the day are usually just pointers, right? So we're getting a pointer to the first element in the list, and we're getting a pointer to the second element in the list, essentially, which is obviously pointing to all the other elements. And so when we do self.slice, we're writing in a number. So setting a number in a field somewhere. So this shouldn't be expensive at all. And I mean, this probably will be inlined and stuff like that, and the slice itself is probably stack allocated, keeping track of where that slice is. So there's a lot of optimization that can be do here. We're essentially ending up with a loop at the end of the day. Great. Okay, so that's all well and fun. There's a question in chat. The wrapper is an iterator. Yes, exactly. We're not iterating over the wrapper. The wrapper is itself an iterator. And in fact, look here. We are implementing iterator for the wrapper. So if it makes us feel better, let's go ahead and do my iterator. So the my iterator is now, it is literally an iterator. All right. Cool. So this is all well and good here, but now is the real challenge, the reason that we're actually here, and that challenge is trying to do the same exact thing, but instead of iterating over an immutable slice and getting immutable references to each element in the slice, let us do the same thing, but with mutable slices and mutable elements. All right. So now we're going to do the same thing, struct my mutable iterator, and it's going to essentially be exactly the same as before. So it's going to be generic over tick A and T. It's going to have one field called slice, and that slice is going to now have a reference in it, but importantly, a mutable reference here. Oh, and So this is just like our myIterator, but now a mutable iterator instead. And an important thing to keep in mind is that this is called mut or mute. It's mutable. But another way to think about it is that it is exclusive. So when we have a immutable slice here, it is non-exclusive, meaning there might be other slices just like this, pointing to the same exact, array of things, pointing to the same exact collection of things. We can have as many immutable, many non-exclusive references as we want. And in fact, same here. Like we have this immutable reference to t here, and the fact of the matter is that we can have as many of these as we want at the same time. And in Rust, the thing to remember is immutable references, you can have as many as you want. They are non-exclusive references. Or you can have one and only one mutable reference, an exclusive reference. All right, so that's really the difference here. We use the term mutable and immutable because that's usually what they allow us to do. We can mutate when we have this type of reference, and we can't when we have this type of reference. But the reason for that is because mutable references are exclusive. So we can mutate because we are the only one pointing to that thing. We are all alone. All right. So let's do the same thing here. We're going to impl, let's do tick A and T iterator for my mutable iterator, tick A and T. Yeah, there's a note and chat about how this is kind of like a read-write lock. Yeah, in a way, what Rust does is encapsulates the idea of a single writer, multiple reader paradigm that you might be familiar with from locks or from databases, where you only ever have either one reader, only one writer, or exclusive, or you have as many readers as you want. This is the exact same thing here, but baked into the language. All right, so now we want our type here, or type item, to be just like before, but a mutable reference to an element t. All right, and just like before, going to implement next here and put to do here. So this is all compiling, and let's go ahead down here and do the same thing and say collection my mutable iterator. Let me bring all this up here, and this needs to be mutable now. And now what we want to do is first do lm equals lm plus 1. We won't be able to do this. The reason for that is because we here are trying to read from collection while we're writing to it. And what did we just say? We can't do that. We can't write to something and also read at the same time. We can either read as much as we want or have one thing write to the thing at a time. So we won't be able to assert here, but then we can do for lm, let's just do assert equal to let's do collection, the first element of collection, or should be equal to 2 now, because in here, what is it complaining about here? We're iterating over and adding 1 to each element, and so the first element in our collection used to be 1, it should now be 2. All right. And if we go ahead and run this, it will fail miserably. My window has gotten too big. Oops. It will fail miserably because we have not implemented next here, right? So it's panicking and we have not implemented next. So that's now what we're going to have to do. So I have a question. Would you ever want to return an iterator type itself, or do you always want to return a concrete implementation of one? What do you mean by returning an iterator type? Let's see here if I can bring over this docs.rs/standard. Let's bring this up here. Go into vec here, go to iter. Where is it? I think it's on slice actually. Iter. If you can look here, when you call .iter on a vector, it returns this iter struct. And this iter struct is very similar to our my iterator struct here. It simply implements iterator. So you can see here in the standard library, they've implemented iterator for iter, which is kind of confusing to think about. But this iter is a struct type that implements iterator, and it allows you to iterate over a slice that it contains inside. In fact, see. Yeah, so they, for iter, since it implements double-ended iterator, they go ahead and use some unsafe in here. But we don't have to do that. So theirs is going to be using a little bit of unsafe, but we're going to try and do everything in safe code. And they do that because they implement double-ended iterator, which allows you to iterate from either the beginning or the end of the collection, which is not, as far as I'm aware, possible to do in safe code, because you have to basically ensure that when you're iterating from the front and the back, they don't kind of cross over each other, and there's no way to kind of encode that safely in the type system. So there's a question, I guess the core of what I mean is, would you ever return a trait from a function? Would you ever return a trait from a function? So you can't return just a trait from a function. Like there's no way to have a function that just returns iterator here. You can return a trait object, but that's not really, it's not in scope for today's stream. Let's just put it that way. There's no reason to return a trait object when you can just go ahead and return a concrete type that happens to implement iterator. Chat is saying you probably could implement double-ended iterator in, yeah, you're right, using split last, and yeah, you probably can. Yeah, so it is probably safe to possible to do double-ended iterator in safe code. I don't think we'll try that today, and the reason that they use unsafe in the standard library is for an optimization, where you don't have to update pointer and length every single call. That's probably true, yeah. All right, so let's get into this and actually implement our mutable iterator here. And first, I think the best thing to do is to try and go about it like we did before, right? So we want to first get the get the first element. Then we want to set self.slice to the rest of the list and return first element, right? And as long as when we get the first element, we're getting, instead of a instead of getting a immutable reference, we get a mutable one, then we should be good, right? So let's go ahead and try that. We'll do it just like we did before, self.slice.get mute here. So this gives us the first element, but a mutable pointer to it, a mutable reference to it. And then we can do self.slice equals self.slice. Oops. Oh, come on. Ah. All right. So this is the same exact code as we had before, except with two changes. Before we were calling get, now we're calling get underscore mute here to get a mutable reference instead of an immutable one. And instead of just borrowing when we tried to get the rest of the slice, borrowing it immutably, we're trying to borrow it mutably here. But this is now not compiling, even though it was compiling with the same exact code above, just with immutable references instead of mutable ones. So let's kind of try and break down what's going on here. If we go ahead and run cargo check here, we'll get some interesting and somewhat difficult to understand errors here. So it's saying, I cannot infer an appropriate lifetime for auto ref due to conflicting requirements. And when you see this conflicting requirements thing here, you should think to yourself, okay, I've written some code that doesn't necessarily make sense because the code that I've written says that two different things should happen at the same time, which is not possible. So let's take a look at what that is. So first, the lifetime cannot outlive the anonymous lifetime #1 defined on the method body. Okay, what the heck does that mean? Well, whenever you see this thing about anonymous lifetimes, usually what that means is you have some reference here that you have not explicitly marked with a lifetime. And in fact, if we look at this here, the next here function here, we have a reference here to self, but we've not marked that reference with any lifetime. There's no tick, whatever here, right? So that's what it's referring to when it says an anonymous lifetime. There is a lifetime here. All references have lifetimes, but it's anonymous. We're not being explicit about it, right? So, okay. The lifetime cannot outlive the anonymous lifetime defined on the function body. What this means is the amount of time that this borrow lives for when we're borrowing the first element of our list cannot live longer than however long we're borrowing self for, okay? So let's look at the code real quick and think this through. Think what that means. We are borrowing my mutable iterator for a certain amount of time. And in fact, we can go ahead and annotate that right here and say, we are borrowing self here for some lifetime that we've called tick next, which is basically however long the next function is called for. So we're borrowing self for just however long next lasts for, the function next. All right. But when we borrow from self.slice, it's looking and saying, okay, self is borrowed for however long the next function lasts, which means that slice is in turn borrowed for however long the next function lasts, which means that when we reach in and get this first element here, we can look at it for however long the next function lives for, right? But, and in fact, we can just copy this, remove this code, because the reason that is not compiling is a different reason. We're returning that reference from next. So what we've said doesn't make sense here. We want to return an element here that we said should live for however long my mutable iterator lives for. However long this struct lives for, this element should live for. But we are borrowing that element only for however long this next function actually lasts. Whoa. And obviously the next function is going to be called multiple times and stuff like that. This next function lasts for a much shorter amount of time than the Mutable Iterator lives for. And in fact, when we look down at our code here, here's my Mutable Iterator right here. It calls next every time it loops through, right? So it's calling it 4 or 5 times, or 4 times here. But the Mutable Iterator struct itself lasts for all 4 of those calls to next, right? So we have conflicting goals here. We wish to return an element that lives for as long as the Mutable Iterator struct lives for, but we're returning an element that only lives for as long as this next method lasts for, which is a much shorter time. Does that make sense to everybody? That's exactly what this error message is saying here. It's saying, I don't know how to do this because I need the thing that I'm borrowing from self.slice to last just as long as this lifetime here, which we've now called next. And in fact, let's run it again. And we should get a little bit nicer of an error message. So it's saying, first, the lifetime cannot outlive the lifetime next. So however long I borrow this for cannot outlive the lifetime next. This is so that the reference does not outlive borrowed content. Meaning I'm borrowing self.slice for tick next, but the lifetime must be valid for lifetime A. And that's however long my Mutable Iterator lives for. Let's go ahead and change this name here to be a bit clearer. This is where giving actual meaningful lifetime names can be very helpful. This right here we'll call tick iter. This is the lifetime for how long our iterator actually lasts for. And now it should become a little bit clearer what's going on. So self.item here, or self-item here, is a reference that lives for however long the iterator lives for. But what we're returning here is essentially this. Option tick next t. Oh, and this needs to be mute. And this really makes the thing angry. We are returning an option of a reference that lives for however long the next function lasts for, in a place where we need to return a reference that lives for however long my Mutable Iterator lives for. All right? And we can't do that, right? What would happen if we could do that? Well, it's possible if we could do that, that this mutable reference here might be invalidated, or in fact, what would happen here is we would hand out multiple we could potentially hand out multiple mutable references to the same element at the same time, which we can't have, right? We can't have multiple readers at the same time. All right. Let's go back one step here, and please let me know if you have any questions about this. This is why I'm doing the stream. This is a very kind of like, if you understand this, then you're really starting to get lifetimes in Rust. All right. Okay, so let us also look at this error message here. This should be a slightly different error message. So cannot infer an appropriate lifetime for the lifetime parameter in the function call due to conflicting requirements. Again, we're doing something that we should not be doing. We're trying to do two different things that don't really make sense together, right? So we're borrowing self.slice here for next, for the lifetime next, just like we were doing up above. But then we're writing into self.slice here, and self.slice here has to live for however long the iterator lives for. So in a way, it's exactly the same error that we had before, just happening in a different kind of way, right? We are trying to reborrow something for a shorter lifetime than what it needs to last for. So the question becomes, can we borrow an element, or can we try and borrow this element for however long iter lasts for then? If we could try and borrow this element for a time that matches the amount of time that iter lasts for, then things would work out. So we need some way of kind of disconnecting the first element from our slice and saying, I need this thing not to last just for, I don't need to borrow this thing for however long the next function lasts for. I need to borrow this thing for however long the slice, the inner slice itself is borrowed for. Now you might be wondering, okay, well, why did this work up here? And in fact, let's go back to the old way that we wrote it before. Self.slice.get 0. And I'm going to ignore real quick that this will actually panic at runtime. We talked about that before. And then this is the element. Self.slice is equal to 1 there. Sorry. And we return back the element. So this compiles just fine, even though it's effectively the same thing that we did before, except with immutable borrows instead of mutable ones. Why is this working? Well, this is essentially working the same exact way as down below, but because we're working with immutable borrows here, the immutable borrows can effectively be lengthened out to the lifetime of self itself. Because there's no problem in borrowing multiple times into the same thing. Because you can have as many immutable borrows as you want at one time. This is the one place where I'm kind of lacking the kind of formal reasoning around why this exactly works. So if anybody has any good kind of words for, formally why this is sound here, then that would be really great to share right now. But essentially, when we're borrowing self.slice and borrowing the element inside of here, the borrow checker is capable of noticing that we're borrowing it immutably, and then it can lengthen out the borrow that it lasts for until the lifetime of self itself. All right, and there's some people in chat saying, I don't think it's possible to implement mutable iterator without it. Let's say specifically your implementation could hand out mutable references to the same element, but the type system doesn't have a way to prevent that. No, there should be a way around it. So that's what we're going to get to here. And this should prove to those who are kind of just trying to follow along here that this is a non-trivial piece of lifetime code here. So there are some Rustaceans in the room who have probably been writing code for quite a while and are not exactly sure how we would go about doing this. So so this is great. If we can come to an understanding here, then we should be able to think about most lifetime code as it exists out there. And in fact, this caused me when I first saw this on Zoom, or sorry, on Zulip, to pause and really have to think through why this works, even though I write Rust every single day. So again, if you can understand this code, you're well on your way to understand almost any lifetime-based code that you'll find in Rust. And then chat is saying it doesn't lengthen the borrow. Well, it's not really true, and I don't want to dive too much into like the pedantry around why this works. The nice thing about Rust is when it works, you don't have to think too hard about why it works, because the compiler's protecting you from doing anything too wrong, right? But self here is not borrowed for tick A, right? Self here is borrowed for some anonymous lifetime. Again, we can make it non-anonymous, call it next here. So this is just like the code we had before. Self is borrowed for next here. Slice, therefore, is borrowed for next here, and therefore we should only, like at first it might seem that we can only borrow the element inside of slice for next here, but the compiler is able to understand that it can, in a sense, maybe lengthening is not the right way to think about it, but in a sense it can see through that and see that it can last longer than tick next here. And chat is saying, why not declare tick static and be done? Well, that's also possible, but then your iterator is not very not very useful then. And chat is saying, does this mean that the compiler deduced that tick next is equal to tick A? That is a possible theory, yeah. I'm not so sure. I think that is probably right. So then chat is saying tick next exists as much as my iterator does. So the length of time that we're borrowing my iterator for is the same length of time that my iterator itself exists for. That's another possible thing. Again, to be perfectly honest, I'm not exactly 100% sure what the formal reason is for why that code behaves that way. But again, the awesome part about it is you don't really have to be 100% formally sure about it, because the compiler will protect us when it's doing something wrong. And we can think through why this code should work, right? It's fine for us to have to look at an element when we are already looking at the rest of the elements. We can have as many of immutable views into a series of elements as we want at one time. So kind of at a high level, it makes sense. All right, there's a little bit more discussion in chat, but I think we'll stop with the formal reasoning discussion for now and get back to how do we make this code actually work here and see if we can get it to work, because there's a question about whether we can get this to work here. Can we actually get my mutable iterator to work properly without the use of unsafe? And the way that we should be able to do it is by reborrowing the slice. So saying we're going to get a borrow, and this is where double pointers can be very confusing when you're coming into languages that have pointers in the first place, where we have a reference to our slice here, right? So we're going to reborrow this. And then essentially what we want to do is convince the compiler that when we're working on the element and splitting, when we're working on the slice and splitting it apart, that we're doing it in a way that is not messing is not leaving the slice in a temporary illegal state. And that's an important thing to remember with Rust, is that in Rust, even if we could try to convince the compiler that from the beginning of our function to the end of the function that our code is sound, the fact of the matter is that for various reasons, many of which are related to things like panicking and stuff like that, our code always has to be sound. Every single line of our code has to be sound. It may not be always leaving our struct in a correct state from the point of view of our business logic, but from a memory point of view, we can never have any point in our code where our types are not in a correct state from a memory perspective. And so we can pull a trick here and basically temporarily switch out our slice for another slice, work on the slice that originally was inside of my Mutable Iterator, get it into a state, and then once we get into a correct state, then plop it back into to my Mutable Iterator. So let's take a look at the code real quick to see what I mean by that. And I'm going to go ahead and plop down to do here so that the code should hopefully always continually compile. So what we want to do is temporarily replace self.slice with something else so that we can work on what was originally in self.slice and do something with it, all while leaving self.slice kind of in a good state. So we can do that with studmem replace and pass in our slice here and replace it with an empty slice. So what this code does here is replace self.slice with an empty slice. So at this point, after this line of code, self.slice is empty. And what was previously self.slice is now available to us inside of this slice variable here. All right. And now, this slice variable here, what lifetime does this have? Well, this has the lifetime of tick iter, right? So this slice here lasts for however long my Mutable Iterator lasts for. So now we can operate on what was previously self.slice in a way that allows us to do whatever we want to, as long as we operate in the bounds of the lifetime of tick iter here. And Chad is saying this is the thing that sort of unfortunately rarely occurs in the heat of the moment. Totally. This takes a lot of time to kind of be able to reach back and into this bag of tricks. And I would say when you're trying to build up muscle memory for this stuff, never forget about studmem replace, studmem swap, things like that. If you run into an issue that you can't fix, start thinking, can I use these functions in studmem to actually solve this? Start thinking through that. And maybe you won't be able to come to a solution, but if you ever run into a borrow checker issue and you've not thought at least about whether studmem can help you in that situation, then you're kind of doing yourself a disservice, right? All right, so now that we have this slice here, and this slice is going to last for however long my mutable iterator is going to last for, then we're basically back into the situation that we want to be. We can do what we did before. We can use our our friend here, split first, for instance. What is it complaining about here? Oh, it's option, of course. And we, sorry, it should be split first mute here. And now we can write self dot. So now we're going to rewrite to self dot slice and replace it with rest. So sure, between this line and this line here, we were ending up in a place that wasn't right from a business logic point of view, but from a memory point of view, it was totally fine, right? So now self.slice is back to where it should be. It's pointing to the rest of the list, and we can use first here and say sum first. Oops. And this compiles. So we were able to implement a mutable iterator and purely safe code. And the way that we did that is, in a way, we kind of cheated. We temporarily replaced self.slice with a dummy variable in order to get kind of full access to the thing that self.slice was previously set to. Now, any questions about this? And if you understand this, then congratulations. Like, lifetime shouldn't be an issue for you. If you somewhat understand this but don't feel like that you would be able to reproduce this on your own or be able to see when to use this in your own code, don't worry about that too. We were having a discussion in chat before about whether this was even possible, and some people were saying that it wouldn't be. That's because maybe they didn't think about this particular way of achieving it, which is, to be perfectly honest, I mean, I don't know if I would have seen this because I saw the code, on Zulip. Somebody had already written it then, not quite like this, but similar to it. So potentially. So we've ended up into a place where it works, but it's not completely obvious why it works. Oh, it looks like we have a raid. Welcome, everybody. Unfortunately, we're coming kind of to the end here, but I'm going to wrap up and kind of go over this code again. So if you want to stick around and see some Rust, then by all means, welcome. But we are kind of coming to an ending point here. Then chat is asking, can you explain the 2 consecutive let slice lines? In Rust, shadowing variables is totally legal. If it makes you feel better, because you're not used to a language that allows you to shadow variables, then you can do this. This is essentially the same exact thing. But you can overwrite variables, shadow them in a way like this. But this is also fine. This is exactly equivalent to what we wrote before. Hopefully that makes sense. If it doesn't, let me know and I can try and explain it another way. Yeah, and there's a note that's like, I knew about std mem replace, swap, take, all these kinds of things in std mem, but it didn't understand that it would allow me to lengthen the lifetime, and that's essentially, it's not really allowing you to lengthen the lifetime. That's not that you said that, but that's kind of how it came out of my mouth here. What it's doing is writing in this value from source to where your slice was pointing to before and giving you back that slice. So it's just giving us this element here, and this slice here lives for iter. So once we have access to this type, then we have access to a slice that lives for iter long, and we can do whatever we need to do. That's the key there, is we really just want full access to, we don't want to borrow self.slice. We want to own self.slice. And that's the weird thing to think about, because this is a reference, right? It is itself a borrow, but the same thing where we can borrow owned values, we can also borrow borrowed values, right? That's a double pointer, right? And so when we call self.slice here, we are borrowing self.slice, which itself is a borrow. And that's not what we want. We want full access to this slice. We want to be able to do with it whatever we want to. And that's what stdmem replace allows us to do, is say, hey, set this thing to an empty list and let me have full access to it so I can do whatever I want with it. Does that make sense? So does this replace the pointer and the value on the heap? So first of all, there is no heap involved here. This is all kind of, none of this is heap allocated. Okay, I guess the elements themselves are heap allocated, but everything else is stack allocated. So when you think pointer, you shouldn't necessarily think heap, right? You can have pointers to things on the stack. What it is doing here is replacing the pointer that lived inside of this slice field with another pointer. A pointer to an empty list. So essentially like a null pointer, a pointer where we just make a promise, okay, never use that pointer. And then we get full access to the previous pointer, which was pointing to all of our elements, and we can do whatever we want with it, including breaking it apart, which is exactly what we do at split first mut here. All right, so I'm taking this very slowly, but it's probably for a lot of people still extremely fast. So I want to go back through one last time to explain the full code that we looked at today, to explain how things work. And I'm going to post this to YouTube as well, so feel free obviously to watch it again. Let me know if you have any questions as well, and I'm happy to answer them. And again, this is kind of real tough stuff when it comes to lifetimes in Rust. So if you understand this, you're really well on your way to understanding basically any Rust lifetime code that you will see. All right. So the first thing that we did is we had a myIterator struct that simply racked a slice. And of course, we have to then tie the lifetime of the myIterator struct to the lifetime of the slice inside. So these two things, however long the slice lives for, myIterator will live for as well. All right, they're basically tied together. Then we're going to implement iterator for myIterator. All right, and it's going to, when it iterates, it's going to yield out elements that are references to elements that live for however long myIterator lives for. Right. So again, we can't have an element that lives for longer than myIterator lives for. They're tied together. They have the same lifetime. In fact, we can see that. Tick A here, all the way down. And so for the immutable case, it's pretty easy. We can call self.slice.get to get the first element here. Then we can just set self.slice to be the rest of the slice. And we return the element. Now there's some, this will panic if we were to run it at runtime if this, when we get to the point where self.slice is empty. So this is actually a better way to write it. Whoops. Here, where we call self.slice.split first, which simply splits the slice into the first element and the rest of the elements. And this checks if the slice is empty, and so it will return an option, and we can simply use question mark here to say, hey, if it's none, return early here. And then we set self.slice to rest and return our element. So these are equivalent to each other, except we get a built-in check for the empty slice here. All right. Now, when we go to do mutable iterators, we have the same exact thing. We're using nicer lifetime names, and I encourage people to use lifetime names. Tick A is great when it's simple stuff, when you don't really want people to care too much about the lifetimes, when it's obvious. But in this case, where lifetimes might be a little bit tricky and you want to be explicit about them and how they relate to each other, giving them nice names is very important here. So we're giving this lifetime, the lifetime of our inner slice, the lifetime of our iterator, tick iter. That's however long the iterator lasts for. And then here, when we implement it, we know that the element that we're yielding when we iterate lasts for however long our iterator itself lasts for, right? And then we have to pull a little bit of a trick here, because if we tried to implement it in the way that we did before, where we borrow the inner element with self.slice.getMut here, we would try to borrow tick next. We would try to borrow the element for tick next lifetime, because that's how long the borrow of self lasts for. But we want to borrow it for tick iter, and they're not the same lifetimes. So instead, we pull a little bit of a trick where we say, okay, I really need to operate fully on this slice right here. What I'm going to do is replace it temporarily with an empty slice. And then I get access to this slice and I can do whatever I want with it. I have full access here. In a sense, I own this reference, which is, again, a bit of a weird way to think about it because it's a reference. We don't think typically about owning references, but that's what we're doing here. We're owning this reference. We can do whatever we want with it because we own it. And so we can call split first here and do what we did up above. And we can write to self.slice here with the rest here, right? So yes, it is true that on this line, on line 28 right here, self.slice is going to be empty, but that's fine. We always keep self.slice correct from a memory standpoint, even if it's not necessarily correct from a business use case standpoint. But it doesn't matter, right? It's fine. All right. Any questions about this? Again, go over the code, try and see if you can understand why it's working. And in fact, we got into a discussion earlier about we weren't 100% sure. We were sure why this code here doesn't compile, but there was some discussion about why the code up here is allowed to compile. What is the formal reason for it? And we didn't really come up with at least in my opinion, chat may disagree with this, we didn't come up with a really 100% satisfying answer for that, for why this what is the formal reason for why it compiles. Now the high level reason should be clear. Like, we can borrow the first element for however long we want to, as long as, all the way up to however long the slice itself operates for. And chat is saying, without comments, I kind of get this. I wouldn't see a problem with doing it from a logic standpoint if it was commented. Okay. Yeah, if this were production code and in this particular, when you're doing something to kind of get around a lifetime issue, then it's probably a good idea to write some comments. So I would definitely agree to write some comments here about why you're temporarily replacing self.slice so that you can operate on it. All right, that's it for today. I have one last request from everybody. It would be super amazing if you could go ahead, if you like the content that I'm doing on Twitch. I'm trying to do it every week. It helps me a whole lot if you can go ahead and subscribe or follow me on Twitch. And it lets me know that people actually want to watch this stuff. So please, if you can, and I hear some people doing that already, thank you very much. Please go ahead and do that for me. That really helps me out because it lets me know that people actually want to see this. So if you want to see more of this kind of stuff, please give me a follow. Let me know. You can see up above at the very top of the screen my GitHub handle, my Twitter handle, and where you can find me on YouTube as well. If you're watching this on YouTube later on, I'm on Twitch right now. It's twitch.tv/Ryan Levick, all one word there. So you can search for me and watch me live. And I tweet about it when I'm going to do it on Twitter. So make sure to follow me there as well. I know it sounds like I'm just asking everybody to be my friend, but really does help me to stay motivated and to produce more of this material. So I really appreciate that. Cool. Well, then I think that's it for today. I'm going to go start enjoying my weekend, and I hope that everybody else has a good weekend whenever that one arrives. If you happen to be in the US, unlike me, or if you're a US citizen, then remember the election is on Tuesday, so please go vote. I just got word that my vote was counted, so I'm very happy about that. I hope everybody who's not in the US still has a lovely Tuesday next Tuesday. And without further ado, I hope everybody enjoys their weekend, and I'll see you next week. All right.